You watch a high-end robotic arm, like thread a needle, or a manufacturing line moving so fast the parts just blur. And you see this effortless grace.
Right, it looks like absolute magic on the outside.
Yeah, exactly. But if you strip away the casing, what you're actually looking at is a machine constantly trying to stop itself from, well, tearing apart under these incredibly violent physical forces. Welcome to today's deep dive. We're unpacking a highly technical engineering dossier on precision transmission and gear reducer systems.
And the main takeaway from this dossier is that true precision design begins with this almost obsessive demand on every single parameter. I mean, every millisecond of movement is a massive balancing act of physics, thermodynamics, and chemistry.
So let's actually put you, the listener, right inside one of these systems and just run a stress test. We hit the power button. The motor wants to accelerate instantly to hit its programmed position, right?
It does, but before the arm even moves a millimeter, the motor hits a physical wall. And that wall is the mass moment of inertia.
Okay, so inertia, that's just the system's inherent stubbornness, basically.
Exactly. The load wants to stay perfectly still. If the motor's power isn't perfectly matched to that resistance, what we call the inertia ratio, the system's dynamic response just collapses.
Wait, so if the goal is extreme control and, like, high-speed positioning, is matching that inertia ratio between the motor and the load the single most critical factor?
It's definitely up there.
Yeah.
If they don't match, the motor draws massive amounts of electrical current trying to force the movement. And that leads to instant motor overload
Yeah.
or just a severe lag in positioning.
Right. I imagine it's like trying to grab a fully loaded spinning merry-go-round and immediately shove it in the opposite direction.
Oh, absolutely. The physical strain is huge.
Yeah.
But let's say we calculated the inertia perfectly. The motor spins, the gears engage. If those gears aren't held in absolute rigid alignment, none of that math matters.
Which brings us to the actual mechanical assembly, specifically axial play.
Right. Axial play or end play. It's any microscopic physical movement of a shaft back and forth along its own axis.
Basically, if the physical assembly is loose.
Yeah, and that tiny wiggle tells you everything you need to know about the health of the bearing preload. Because if there's too much play along that axis, the gear teeth aren't striking exactly where they were designed to.
They hit, like, slightly off-center.
Exactly, and that microscopic misalignment creates these high-frequency vibrations. Over time, that just shatters the geometric precision of the metal.
Wow. And I'm guessing that vibration only compounds as we speed things up?
Oh, drastically. Let's accelerate our stress test to, say, 5,000 RPM. At those speeds, we introduce a totally new enemy churning loss.
Churning loss. Okay, but wait, don't the gears just slice cleanly through the lubricating oil inside the gearbox?
You'd think so, but they really don't. Above 5,000 RPM, the fluid resistance of that oil rises exponentially.
Oh, so they're physically fighting the oil.
Yeah, they have to drag themselves through the lubricant. It actually becomes the #1 non-mechanical cause for a drop in efficiency. And obviously, it generates a massive amount of internal heat.
Okay, well, if churning loss is creating all this internal heat, we just need to design the gearbox to breathe, right? Just, ventilate it so the heat escapes.
You can't really do that. Think about a robotic arm operating in a food processing plant. It requires an IP67 ingress protection rating.
Oh, right, because it has to survive those high-pressure chemical washdowns.
Exactly, without letting a single drop of water or speck of dust inside. Otherwise, you short-circuit the electronics or corrode the metals.
So wait, to protect it from the outside environment, you are essentially trapping the system in a watertight oven.
That is exactly what happens. A watertight oven where the mechanical stress and the trapped heat are actively pushing the physical properties of the lubricating oil to their absolute breaking point.
Right, the oil gets so hot and thin that the physical film separating the gear teeth literally just vaporizes.
Which is terrifying, really, because when that physical oil film ruptures, you are milliseconds away from raw metal grinding against raw metal.
Which causes micro-welding, right? Like instantaneous mechanical failure.
Yes. But that is exactly where tribology steps in, the science of friction and wear. It acts as the ultimate chemical failsafe, specifically using anti-wear, or AEW additives.
Oh, so these additives do something the oil itself can't?
Yeah, they are thermoreactive, so the localized spike in heat from that impending metal collision actually triggers a chemical reaction.
Wait, really? The heat of the failure makes them activate?
Exactly. They instantly bond with the metal to form a microscopic sacrificial chemical scab over the gear teeth.
A chemical scab. That's wild. So it gives you a protective layer precisely when the mechanical layer fails.
Right, it saves the whole system. When you look at the parameter impact matrix for a machine like this, it is basically a house of cards. You miscalculate inertia, the motor fries,
You allow axial play, the gears vibrate themselves to death.
and you underestimate churning loss inside a tightly sealed IP-rated casing. Well, you cook the machine.
It's incredible. Everything has to be managed simultaneously just to get that simple needle threaded on the outside, which really leaves you with a fascinating paradox to think about.
It really does.
As we engineer smaller and faster robotic joints for the future, how exactly are designers going to solve the problem of needing even tighter IP seals against harsh environments while somehow safely dissipating the explosive heat of high-speed churning loss? The obsession under the hood is clearly only going to get deeper.